All right, welcome everybody. So far we've been looking at recently vector spaces and subspaces of vector spaces. And so on this slide, what we are looking at is, well, let's consider our vector space V to be R3 with all of the usual operations of vector addition and scalar multiplication. And let's consider the set below that has 5 different column vectors in R3. The first vector is 1, 0, 0, the first standard column vector. Then we have 0, 1, 0, the second standard column vector, 0, 0, 1, and then the vector 1, 0, minus 1, and then lastly the vector 0, minus 2, 5. So here we have a set of 5 vectors. And recall from what we just discussed about vector spaces and subspaces, and that is if I were to take the span of these 5 vectors, call this space H, this is going to be a subspace of R3. So the question that we might ask is, does this set span all of R3? And secondly, do we need all of these vectors in order to span this full space? So the first question is saying, okay, do these 5 vectors span all of R3? And notice that this set contains standard vector E1, standard column vector E2, and standard column vector E3. So they are going to span all of R3 because any vector B that we define in R3, let's just say it has components B1, B2, B3, we can write this as a linear combination of the 3 standard column vectors. We could write this as B1 times 1, 0, 0, B2 times 0, 1, 0, and B3 times 0, 0, 1. So these set of all 5 vectors, they do span all of R3. And so the next question that you might ask is, well, do we need to include all 5 of these vectors in order to span R3? Our argument to answer this first question didn't involve these last 2 column vectors at all. I didn't need the vector 1, 0, minus 1 or the vector 0, minus 2, 5 in order to be able to generate any vector in R3. So now our question is, well, let's construct, let's say, the most efficient set of vectors that are going to span this entire vector space. And so when I say efficient set of vectors here, I mean the least amount of vectors that we need. And so we do span all of R3 with this set of 5 vectors, and we really just needed the first 3 vectors in order to do it. And so let's see why that is. So this last column vector, 0, minus 2, 5, right? We can express this as a linear combination of standard column vector 2 and standard column vector 3. I could write this as minus 2 times 0, 1, 0 plus 5 times the vector 0, 0, 1. Similarly, this fourth vector that we had in here, 1, 0, minus 1, we can write that as a linear combination of standard column vector 1 and standard column vector 3. We can write 1, 0, minus 1 as the vector 1, 0, 0 minus the vector 0, 0, 1. So these last 2 vectors are linear combinations of the first 3. So we really don't need this vector, and we don't need this vector over here in order to span all of R3, because these 2 vectors are already in the span of the first 3 vectors. So just some points to observe here, and that is, well, if we remove these 2 vectors that I just highlighted in red, then we do not change the space that we're able to span. We still span all of R3. Removing one of these standard column vectors, however, in addition to just these first 2, so if I remove these 2 and say, well, why can't remove another vector? Do we need even all 3 of these? Well, if I remove any one of these remaining 3 vectors, then we're no longer going to be able to span all of R3. For example, if I get rid of standard column vector 3, we would not be able to get any vectors in R3 that have a non-zero entry in the last component. So we do need all three of these vectors here. We can't remove any more vectors from our set. So we need a minimum of 3 vectors to span all of R3. These 3 vectors would do the trick. So in some sense, these 3 vectors form the most efficient set of vectors that we need to span R3, and that this is the smallest number of vectors that we would need to span R3. And so you might be thinking, can we choose other vectors, maybe another set of 3 vectors that we could use to span R3? And yes, we certainly can. So this is not unique. This is a particularly nice set of 3 vectors that we can name to span R3, but we can pick other collections of 3 vectors that might span all of R3, but just picking any random 3 vectors is no guarantee that we're going to be able to span R3, because we want to make sure that we don't have any linear dependence between the vectors in our set. And since I just referred to this term of linear dependence, I just want to review those definitions before we move further in this section. So if we have a vector space V, and we have some indexed set of vectors, set S, which consists of vectors v1, v2, all the way up to vp. So we have a set of p different indexed vectors, and these might be column vectors, or they could be more abstract vectors such as matrices and other vector spaces that we've looked at. The set of vectors in S is linearly independent if the vector equation c1 v1 plus c2 v2 ... all the way up to plus cp vp equals the 0 vector has only the trivial solution. So if the only way that we can take a linear combination of these p vectors in this set and wind up with the 0 vector is if we were to pick all of these weights, c1, c2, cp, all of these weights have to be 0. If that's the only solution to this equation, then these vectors are linearly independent. On the other hand, if this same vector equation does have a non-trivial solution, then we say the set of vectors is linearly dependent. And an equivalent way of thinking about this is thinking about linear combinations of vectors. And so down below, we have this theorem that says if this same indexed set of vectors, v1, v2, up to vp, where we are going to assume we have at least 2 vectors in this set. So we at least have a v1 and a v2, where the very first vector is not the 0 vector. So this set of at least 2 vectors is going to be linearly dependent if there exists some vector in this set which can be written as a linear combination of the preceding vectors. So essentially, this set of vectors is going to be linearly independent if any one of these vectors in the set cannot be written as a linear combination of all of the other vectors in the set.